Another thing we can do with Wireshark is we can set a time reference. So for example, in this trace I've opened up called Download Both. Right now I've got the time value set for seconds since the beginning of the capture, and I've got the file format precision set to automatic. In packet number 4, I see a handshake packet taking place between 10.0.52.164 and this server at 216.251.114.10. I know that this ends around packet number 247. And I want to find out exactly how long that process took. So in this case, I'll right mouse click on packet number 4 and set a time reference. Now all packets that arrive after packet number 4 will be set in time compared to when packet number 4 arrived. Now I'm going to go to packet number 247, which is the end of that HTTP communication. And now I can see that this packet arrived 11.448561 seconds later. So that way we can use a time reference to figure out how long it took between one packet and another packet. Another nice thing we can do if we set time references through the trace is that we can use the edit feature to find a time reference that occurred earlier or later in a trace. So we can go back to the previous time reference very easily this way. Now the last function that we can use time for is if we set the time display format to give us the date and time of day, or just standard time of day here, and that's going to be based on what your system is set for. So make sure that if you travel with Wireshark that you just change your time zone setting. You shouldn't have to go and change your time setting, just go and change your time zone. If I select this first option, it will now show the date and time values in this trace file. So this trace file was taken at on November 2nd, 2005 at 6:58 p.m. and 12 minutes. The timestamp column is extremely important and extremely valuable in Wireshark when we're doing any sort of troubleshooting in particular, or maybe even we're working with security and we're seeing a really very busy scan on the network. By default, the time column will sit next to the number column, and the default setting is to show us when the packets arrived compared to the first packet in the capture. So the first packet in the capture will show up with a timestamp of 0, and then every other packet that arrives, once it's completely arrived, it will be timestamped by WinPCAP in the Wireshark for Windows version, and then that will be passed up to Wireshark. Wireshark will figure out what the exact time is, such as the date and the time, based on the time value that's piped up from January 1st, 1970, the number of nanoseconds since midnight, and that's the format that it keeps it in the trace file. Now you need to know that the operating system kernel is what passes that timestamp value off to WinPCAP, which in turn hands it over to Wireshark. Again, that default setting is going to show us when each one of these packets arrived compared to the first packet in the trace file. So if we go to the end of the trace file, we can see that this trace file is 40.838548 seconds long. That default timestamp value may be fine if you're working with something like this where I have a web browsing session going on, and I can see that about almost 2 seconds into the trace is when initial handshake packet went out, and I can go all the way to the end of the trace and I can see about 31.78 seconds into the trace is when it finished up. So we can subtract those 2 seconds and say that that process took about 29 seconds to load that page and do whatever other function I was doing. We do have some options that we can change right here, even if we're just using the default time column settings. If you select View, Time Display Format, you'll see that we have various different time stamping formats that we can use, but we also have the ability of saying to Wireshark that we want it to use file format precision. That means look at the file format, look at the type of trace file that I'm opening here, and figure out, does it go down into the microseconds or does it go down into the nanoseconds? If we're not sure when we open up a trace file, we can go ahead and force it to go to nanoseconds. And then when we look at the times column value, we can tell that the last 3 digits there are always 0. So this one did not save in nanoseconds. This one saved only down to microseconds. So if we go back to view, we can go to time display format and force it to show us all the time down to microseconds. There we go. Now we're at our original view. If we just want to get a general idea and we're trying to save real estate on the screen or something like that, we can always go in and even shorten that further. Go to time display format, and then we can say we just want to go to milliseconds, and that'll shorten it down even more. But if you want to, you really probably want to keep it associated with the file format. So it's automatic. It will figure out how precise the time value will be, and it will only show you the precision down to the level that it starts seeing all the zeros at the end. One of my favorite time settings in Wireshark is the time setting that will show me from the end of one packet to the end of the next packet how much time has transpired. So instead of this trace file right now that I'm showing you here, showing me when each one of these packets came in compared to the first packet in the trace, I want to know how much time has elapsed between packet number 1's arrival and packet number 2's arrival. And remember, this isn't really the time between packets because packets are time-stamped when they arrive by when PCAP sees them. So it's actually showing us from the end of one packet to the end of the next. If we want to change the setting, we would just go up to View, Time Display Format, and select seconds since the previous packet. So now the timestamp has changed. So we can see that the first packet's still in the trace. When we use this new timestamp, the first packet in there will be marked as 0. And then the second packet arrived 6.013555 seconds later. And look at the amount of time between packet number 2 and packet number 3. 305 seconds went by. And then 6 seconds after that packet, another packet went out, and then 305 seconds. Whenever you see this kind of time stamping where it's very deliberate and there seems to be a pattern to it, you've got to realize that there's something in the protocol or something in the application that's triggering those retransmissions at a certain time or that specific transmission at that particular time. It's just very unusual that things would happen in such a definite pattern. It just really doesn't happen in networking. Networking traffic is so bursty typically. I want to show you an example of how we can use the time value from the end of one packet to the end of the next when we're looking at traces that have to do with security. I'm going to open up a trace file called port scan. And first of all, the colorization in here is just absolutely awful, so I'm going to get rid of the colorization for a moment. Now here we can see packets going out from 10.1.0.2 going out to 10.1.0.1. It's a handshake packet, and then the response comes back as a reset, which means no, I'm sorry, I don't support that port number. Then we see another scan go out to port number 2, and a reset comes back saying no, I don't support that. Now, looking at this time value setting right now, it's showing us from the end of one packet to the end of the next. It saves that setting, and as you open up additional trace files, it'll save the last time setting that you had. So in here I can see that the time between when the first packet arrived and the second packet arrived is 290 microseconds. That's 290 millionths of a second. If we look at when the next scan went out, we can see that was about 6.5 milliseconds, or 6.5 thousandths of a second later. And as we kind of look through these scans, we can see they're approximately every 5 milliseconds they seem to be going out on the cabling system. Now, if I had left the time display format at the previous setting, seconds since the beginning of the capture, and I were to scroll through this trace file to look at these scans, all of a sudden something changes in these scans. Suddenly we don't see any more resets coming back. Here are the last resets that we saw being sent back, and then all of a sudden we see the scans coming along. And we might not notice what's truly changed other than the pattern of the ports, the destination ports. But if we go over to the time column setting here and we change it so that it shows us the time from the end of one packet to the end of the next, it becomes clear what's changed. Now here I'm up at the beginning of this trace file. Bring this window down a bit. I'm at the beginning of the trace file, and we were looking at these packets, and the scans seem to be going out about every 5 milliseconds. And then all of a sudden we have a 0.7 second delay, almost a 0.7 second delay, and now we can see quite a difference in the time value between each one of these packets. This packet went out 19 millionths of a second after packet number 28. And this packet was seen 17 millionths of a second after packet number 29. So the rate at which this scan is going on the cabling system is just phenomenally faster than the previous scans that were going out about every 5 milliseconds or so. So the time column can tell us a real story. This is my favorite time column setting, and in fact it's my default time column setting, no matter whether I'm doing troubleshooting or I'm doing security work using Wireshark. Another thing we can do with Wireshark is we can set a time reference. So for example, in this trace I've opened up called Download Both. Right now I've got the time value set for seconds since the beginning of the capture, and I've got the file format precision set to automatic. In packet number 4, I see a handshake packet taking place between 10.0.52.164 and this server at 216.251.114.10. I know that this ends around packet number 247. And I want to find out exactly how long that process took. So in this case, I'll right mouse click on packet number 4 and set a time reference. Now all packets that arrive after packet number 4 will be set in time compared to when packet number 4 arrived. Now I'm going to go to packet number 247, which is the end of that HTTP communication. And now I can see that this packet arrived 11.448561 seconds later. So that way we can use a time reference to figure out how long it took between one packet and another packet. Another nice thing we can do if we set time references through the trace is that we can use the edit feature to find a time reference that occurred earlier or later in a trace. So we can go back to the previous time reference very easily this way. Now the last function that we can use time for is if we set the time display format to give us the date and time of day, or just standard time of day here, and that's going to be based on what your system is set for. So make sure that if you travel with Wireshark that you just change your time zone setting. You shouldn't have to go and change your time setting, just go and change your time zone. If I select this first option, it will now show the date and time values in this trace file. So this trace file was taken at on November 2nd, 2005 at 6:58 p.m. So here's an example of how you might use the time column to help you as you go through a trace file and you're troubleshooting slow network performance. This is an example of a trace taken from a system that was experiencing some sluggish behavior, just poor performance. And as we grab the trace, we look at it and we can see that there's some black backgrounds here on some of the packets, which typically mean that some sort of a problem perhaps or an error. In this case, we have some ICMP destination unreachable, port unreachable messages going on. We'll scroll through the trace, and around packet number 20, we suddenly see a request for desktop.ini. We see a response saying no matching files or directories were found. And we see the same request being made again, open or create desktop.ini, with a response saying no matching files or directories were found. And as we scroll through this trace, look at this. We just keep seeing the same thing over and over and over again in this trace. Now we've got public /desktop.ini. Now it's a natural gut reaction to look at that and say, oh, that looks terrible. That's what's causing the poor performance. But what you want to do is when you see something like that and you're troubleshooting slow network performance, you really need to validate that that's the thing that's taking so much time. So go back up to the beginning where we first begin to see all this ugly traffic. So here's the first packet where we see a request for this. Now I'm going to right mouse click and say I'm going to set the time reference on that packet. So packet number 20 is now considered the beginning of time again. I have my time column set right now in the default format to show me the seconds since each packet arrived compared to the beginning of the capture. So I've got that set, and every one of these packets will count up from the time reference now. Now all I have to do is go to the end of this whole ugly process here. And there we go. Packet number 164. So how much time did all this ugly garbage take on the cabling system? About 43 milliseconds. That's probably not the cause of the problem. Now I can tell you that this is the last packet where we saw this desktop.ini request. After that point, it just went on to normal communications. So if we were taking this trace in the background while a user was complaining about performance, we can be pretty certain that this is actually not what's slowing them down, because this only took up 0.043 seconds to actually resolve itself. So now what we're going to do is we're going to get rid of that time reference. We don't need it anymore. We'll go ahead and get rid of it completely, and then we'll reset the time value. So I'll change that, toggle that off. I'm going to go to View, Time Display Format, and this time I'm going to say that I want to see the time set as seconds since the previous packet, from the end of one packet to the end of the next packet. Now when I look in the trace file, if there are areas where performance is slow, I should be able to see them show up in the time column field. I'll tell you, this is a situation where I'll probably get rid of the colorization because I find it very distracting. So I'm going to turn off colorization, and I'm at the beginning of the trace file, and I'm looking for any large gaps in time that show up here in the time column. And there we can see that's actually a big amount of time there, 0.75 seconds. Right here we've got a 1.5 second delay and another 1.5 second delay. And remember, when you see the time so close, you've got to figure that it's most likely a human involved that set some sort of a timing mechanism. And sure enough, this is where we see a workstation go out and do a name query, get an error back, and 1.5 seconds later they do another name query. They get an error back, and 1.5 seconds later they do a third name query. And they get an error back from that, and eventually they move on. So this has the feeling that the problem is not all of these queries for desktop.ini, but the problem is related to these net bias name queries going on the cabling system. They are all unsuccessful, so why are we making those queries? We need to shut that off and get rid of those queries. Now let's take a look at the summary information that you can gather. And you can gather summary information while you're capturing. So I'll begin a capture running in the background. And now I'll go to Statistics and Summary. But this is just a snapshot of the traffic that I was looking at that moment. You'll see that it's not automatically updating. So if I want to see the current information at any point while I'm capturing, I have to go back to Statistics and Summary to see the information at that point. In the summary information, we can see things such as the temporary file where this is being kept, and the length of the file, as well as the format, the packet size limit. We can see when the first packet arrived, when the last packet arrived, and the total elapsed time. Again, remember, this is just a snapshot, so if I want to see the latest information, I have to go back to Statistics and Summary. So here we go. Now I'm looking at the capture interface. Tells me what interface I was using when I captured this. Drop packets unknown. Well, I'll tell you, we're not seeing any dropped packets yet. If we were seeing drop packets, we would be able to tell because down on the status bar, we would have the word drops, colon, and then a number there. Capture filter, I'm not using any capture filter at all at this point, and there's no display filter at this point. I have no marked packets. And then we have the basic traffic information, such as the time between the first and the last packet in the trace, the total number of packets. That was, again, just at the time I took that snapshot. The average packets per second rate, the average packet size. Ooh, look at that little itty-bitty stinking packets. And I'll tell you that's because the majority of these packets in the background are ARP packets. Then we've also got the total number of bytes in that trace, the average bytes per second rate, and the average megabits per second rate. Now I'll go ahead and stop this trace from running. There we go. And I'll apply a filter. Now the filter I'm going to apply will separate out the DHCP traffic. But remember, you can't use DHCP as a filter in Wireshark. You have to put in bootp, and that will cover both bootp and DHCP. So now I've applied a bootp filter on here. Now when I go up to Statistics Summary, when I look at the packet information, the traffic information at the bottom, I'll see not only the captured information, but I'll also see the displayed information based on the display filter that I set. So here you can see the filter that I set was a bootp filter, and between the first and the last packet of the filtered set there was 131 seconds. Total number of packets that are DHCP packets are 41. The average packets per second rate, 0.313. The average packet size, the bytes used for DHCP traffic, average bytes per second, and then the average megabits per second. Now this is really nice when you're comparing apples to apples or oranges to oranges. For example, if I'm comparing a fast download to a slow download, sometimes the summary information can really tell me what's going on by just pulling up the summary of the two trace files side by side and comparing them. The first thing I'll do is I'll close down the summary window, and then I'm going to close out that capture file without saving it. I just want to get rid of that filter right there. Remember, the filters stay with you as you open up additional trace files, and that can be really a hassle. When you open a trace file and you don't see anything, then you don't realize, you look up and you find that you have a filter there. Remember, those display filters are going to be covered fully in section number 8 as well. So I'll clear that out. Now I'm going to open up a trace file. I'm going to open up one called Download Good. Now, this is when somebody was downloading this OpenOffice application from a server, and in this trace file they were happy with the performance. But another time when they downloaded it and we grabbed a trace file, they were not happy with the performance. And we want to compare the two downloads and see what we can learn about the two of them, what might have happened with the poor download process. So now I'm going to toggle over to another instance of Wireshark. Now in this instance, I'm going to leave colorization on just so we can tell the difference between the two instances as we toggle back and forth. And here I'll open up Download Bad. And here we go. So we can see the handshake process, and then we can see the request to open up the trace file. The first thing I'm going to do is I'm going to look at the summary statistics for Download Bad to see how it looks. And here we go. Now there's no filter applied to this, so I'm just looking at the actual download process of that file. And the time between the first and the last packet, 125 seconds. Total number of packets are 7,195 packets, and I should let you know that the user actually aborted the download because they just said they couldn't stand it anymore. And I can understand 125 seconds just for the download process is absolutely ridiculous. Even though that is a pretty big file, that's still crazy. Average packets per second size, average packets per second is 57 packets per second, and that is not very good. The average packet size of 773 bytes. Now, a lot of that may be affected by the number of ACKs that go across the wire. When you're using something that runs over TCP communications, using some sort of a transfer protocol or application that sits on top of TCP, you're going to have a lot of these little tiny ACK packets on the wire. Number of bytes transferred, there we go. The average bytes per second is 44,497 bytes per second. The average megabits per second, 0.356. Now at this point you may want to pause the video so that you can just write down a little bit of this information, because we're going to toggle over to the good download and compare those two in just a moment here. And so I'm going to go ahead and close this window down, and I'm going to go over to the good download. Now you can tell we're on the good download because we've got the name of the trace file up there in the title bar, and I also turned off the colorization in this instance of Wireshark. Now I'll look at the summary information over here and we can compare the two. All right, now at this point we have a download and it's 23 seconds, a little over 23 seconds between the first and the last packet. So I would say yes, this is a lot better download. And we had, in that download process, we had 9,354 packets because the user didn't abort the download process. The average packets per second rate is 402, almost 403 packets per second, whereas in the other trace, the average packets per second rate was 57.539. What a difference. This is 8 times faster right now. The average packet size in this trace is 754 bytes, whereas in the other one it was 773 bytes. Not a tremendous difference. The byte count is going to be much larger because the user did not abort the download in this case. The average bytes per second. In the bad download, the average bytes per second rate was about 44,500. We'll just kind of round it up, 44,500. Here we're at 303,772. Tremendous difference between the two of them. And then the average megabits per second, 2.43 megabits per second, whereas in the other trace file it was 0.356. So there's a big difference between the two. And using that summary window to put items side by side can help a lot.
Now it's time to test yourself using time. These steps are listed in Appendix A, Wireshark Lab Exercises. In step number 1, I want you to open up the trace file called http://slow-filexfer.pcap. Set the time display format to the seconds since the previous packet. As you look through the trace, you're looking for delays in the packet transfer process. Is the client slowing down the transfer process? Step number 4, I want you to determine how long it took to download the file and find out what the average megabits per second rate for the download would be. In some cases in this lab, you may have to change the time value to a different setting. And in step number 5, determine how much time elapsed between the client's SYN packet and the server's SYNAC packet during the connection establishment process. If there's more than one connection establishment process, determine how much time elapsed between each of those. Now would be a good time to pause the video and complete the lab. And when you're ready to see the results of the lab, restart the video.
Now in this lab exercise, we're using a combination of what we've learned using the time information that Wireshark provides and also using the summary information that we can get through statistics. So the first thing we'll do is we'll open up the trace file, and the file is called http://slow-filexfer.pcap. I'm going to leave my colorization on here as I work in this trace file. The first thing you'll note is that the packet time values here, I've got it set for the default to show me when packets arrive compared to the first packet in the trace file. So I don't want that setting. Anytime you're troubleshooting slow performance, you want to make sure that you change that setting over to the seconds since the previous packet. So there we go. Now I'm going to just scroll through here very briefly to look for any sort of delays, and I can tell you that just even to see this sort of a delay right here, a 0.371 seconds between the SYN and the SYNAC packet, that's pretty substantial. But down here we have a 1.449 second delay, almost a 1.5 second delay. Now you might want to take note that the client appears to be the 67.169.189.113, where the server is starting with the byte 65 in the first byte field. So when we see this delay, we want to see who is it that was so slow sending the packet. And it appears to be that the server was pretty sluggish on sending that packet back. And when we see another one, this is another one that seems like it's a bit sluggish here. But this one is from the client, coming from our client out to the server. We're looking for any more of those large delays. Now one way of doing this would be just to sort of scroll through and look for any large numbers. There's one right there, packet number 65. We can see a bit of a sluggish response, 1.6 seconds between packet number 64 and packet number 65. Now you can do it this way, or you can sort the time column. So I'm going to sort the time column, click on it twice so that the arrow is pointing up. Now the larger values in time will show up at the top. And here's one right there. Look at that, 3 seconds. In the middle of what should be an automated process that should come down very, very quickly and has no user interaction required. Once they said they wanted that file and then they hit enter, all of this should have happened in the background and should have been done very quickly. If we look at this setting right here, 3 seconds for this one, over a second and a half, almost a second and a half. All of this really starts to add up, so we can see that this is taking quite a bit of time. So now we want to know how long it took to download that entire file. So I'm going to go back to sorting that number column because I like to keep it in order. And I'll select Statistics, Summary. And in the summary information, it tells me the time between the first and the last packet in that trace is 75.829 seconds to download that trace file. To download that file. Total number of packets, 1,040. The average packets per second rate is only at 13.715. That's not very fast at all. The average megabits per second rate, 0.079. Really, really poor performance. Now I want to see how much time there is between the SYN and the SYNAC at the beginning of that trace. So there's the first packet in the trace. Now at this point it doesn't matter whether you have your time column setting set to show the second since the beginning of the packet capture or second since the previous packet, because both of these values will show the same number in that column right there. So it's 0.371358. So if I go back to the other format where we see second since the previous packet, it's the same value because they're just counting up between the first packet and the second packet. That's the only time you'll see that in the trace, where it doesn't matter which one of those time settings you use. So this is obviously, this trace file's got a lot of problems. And later in this course, in section 7, we will use the expert system to look a little further into this trace file and figure out what happened and why things are slow.